So let us continue our discussion with the definition of an integral domain of finite characteristic. An integral domain D is said to be a finite characteristic if there exists a positive integer m such that ma is equal to 0 for all a in D. Okay, so if we have a positive integer m for which ma is equal to 0 for every element a in D, then D is said to be a finite characteristic. If B is of finite characteristic, then the smallest positive integer p for which pa is equal to 0 for all a belonging to D is said to be the characteristic of D. So if D is a finite characteristic, then there is one such positive integer, at least one positive integer m for which this condition is true. Then there will also be a smallest such positive integer by the well-ordering principle for which this is true. And that smallest positive integer is said to be the characteristic of the integral domain D. It can be proved that the characteristic of an integral domain which is of finite characteristic is a prime number. This p will always be a prime number. In fact, this we will prove in exercise 6. Okay. We have already seen that finite fields are of finite characteristic. Finite fields are of finite characteristic. In fact, that is where we started our discussion by considering this sum where 1 is the unit element in a field. In a finite field where the number of elements in the finite field, if we take that many ones and add them up, then we get 0. This follows from one of the corollaries to Lagrange's theorem from group theory. This is where the concept of characteristic started. So we have seen that finite fields are of finite characteristic, but there are infinite integral domains which are also of finite characteristic. But there are integral domains of finite characteristic which have infinitely many elements. See exercise 7. Exercise 7 asks us to provide such an example. Okay. Now a question may arise, in fact it should arise, is that we started our discussion of characteristic from finite fields, and then while defining the concepts we chose to not just do it for fields but more generally for integral domains. But why did not we generalize all the way to include all rings? What is the problem of defining characteristic 0 or finite characteristic when D is replaced by a general ring? So let's look at that issue with an example. Consider the set R so this is the ring of integers modulo 2, this is the ring of integers modulo 3, this is the ring of ordinary integers. In more popular notation we will write this same thing like this. However, for us Herstein has chosen to denote the set of integers by J, capital J, so we continue to use this notation. On R, we define an addition and a multiplication as follows. So we have chosen any two elements in R. Now we are going to define addition. Addition, by now you already know, having seen so many examples of rings, that if the elements have multiple components, then addition almost always is defined component wise. A plus A prime, B plus B prime, C plus C prime. For now, multiplication will also be defined component wise for this example. Before we go any further, let's just quickly look that this A and A prime are integers modulo 2. They are coming from here. So each one of them is either this congruence class or this congruence class. This is the set of all integers which leave the remainder 0 when divided by 2. This is the set of all integers leaving the remainder 1 when divided by 2. In other words, this is the set of all even integers. This is the set of all odd integers. in J3 we have 0, 1 and 2, but they are different from this. Okay, they are congruence classes modulo 3, not 2. So that's why this addition is integer modulo, addition modulo 2. This addition is addition modulo 3, and since C and C prime are ordinary integers, this is ordinary addition. And similar remarks are true for multiplication. It's easy to see that R is a commutative ring with unit element. That's not very difficult. It can be verified quite easily. And the unit element is nothing but this. Where you understand that although these two look like the same thing, but they are different. This is the congruence class modulo 2 containing 1. This is the congruence class modulo 3 containing 1. Okay. Anyhow, this is the unit element. Now, the important point, this ring is not an integral domain. Note that the elements in R are both different from the zero element. This is the zero element naturally. But their product is the zero element. What this means is that both these elements are zero divisors in R, and because of the presence of zero divisors, R cannot be an integral domain. Hence, R is not an integral domain. So R does not fall in the class of rings for which we have defined those two definitions involving characteristics, since it's not an integral domain. But what happens if we try to apply the conditions in those definitions on R? What do we get then? Note that 3 times 0, 1, 0 is equal to, okay, what is the meaning of this? The meaning of this is that we have to add this 3 times. If we do that, this will be 0 plus 0 plus 0, that is 0. This will be 1 plus 1 plus 1 in the ring J3, and that gives us 0, because this is integer modulo 3. And this again 0 plus 0 plus 0 becomes the ordinary integer 0. So ultimately we get this. Where this is clearly not equal to this. Also, for any positive integer n, we have m times 0, 0, 1. This becomes equal to 0, 0, m. This again is not equal to 0. 0 means the 0 element in the ring R. So what is the significance of these calculations? Let us now recall the characteristic definitions, the definitions involving the concept of characteristic. We say that an integral domain D is of characteristic 0 if whenever I choose an integer m is an integer, and any non-zero element a in D, then ma equal to 0. This statement implies m is equal to 0. If this is true, then we say that D is of characteristic 0. Now if I replace D by R, then I get a new definition actually. The new thing here is that instead of integral domain, I am considering a general ring, and I apply this definition in this case. Is this ring is this particular R of characteristic 0? For that, what should I have? If I choose any integer m and any non-zero element a in R, this must imply this. However, you see this calculation here, 3 times this non-zero element 0, 1, 0 is equal to the 0 element of the ring. So that means I am having ma is equal to 0. Note that here this is a is non-zero, and this is my m, but still I don't have 3 equal to 0. So that means this does not imply this. Because in this implication the hypothesis is true but the conclusion is false. That means the implication is false. So if I try to generalize the definition of characteristic 0 to a general ring, then my particular ring is not of characteristic 0 in the general sense. Now we come to the similar thing for finite characteristic. I say that an integral domain is of finite characteristic if for every, if there exists a positive integer m such that ma is equal to 0 for all a in D. Okay. Now this also, if I generalize to an arbitrary ring R and apply this general definition in our particular ring, what do I get? I don't get this actually. Why? Because you see here, I should have a positive integer m such that ma is equal to 0 for all a in R. But if my a is this, then no matter what positive integer I am choosing, see, for any positive integer, this product will never be equal to the 0 element. So that's why my ring R is also not of finite characteristic. So we cannot generalize to these two definitions for a general ring which is not an integral domain. However, you will see in literature that characteristic has been defined for general rings in this way. Okay, for this I need to say some things. Suppose you have a group G, right? Now, suppose this group has a particular property. What is that property? Whenever we choose any element in the group G, then that element has finite order. If that happens, then G is said to be a torsion group. Such groups are called torsion groups. In particular, finite groups are torsion groups, but there are infinite groups which are also torsion groups. Now, so that means every element has finite order. Now, suppose it happens that there are only finitely many possible orders. Say the original group may be infinite, but say all the elements are of order 1, 2 or 3. I am just taking an example. Okay, this actually may not happen. 1, 2 and 3. Then we can take the LCM of those orders. The LCM, if it exists, that is, if there are finitely many orders available, then the LCM will exist. Then that LCM is said to be the exponent of the group. Using this concept of exponent, we can define characteristic of a general ring, but it may not always exist because exponent may not always exist. And what is the group that we will use in this case? The group is the additive group of the ring. You can define the characteristic of a ring to be the exponent of the ring whenever it exists. If there is a finite exponent, then we say that that is the characteristic of the ring, in which case it is finite. Otherwise, we say that the ring has characteristic 0. This is something somewhat different from what we are doing here, and for us we are defining characteristic for integral domains. Okay, so that much I had to say. But Herstein does mention something else. So okay, let me summarize here. So the definitions of an integral domain being of finite characteristic or of characteristic 0 cannot be generalized to an arbitrary ring. One thing that you should that we should observe is that our definition of characteristic 0 is slightly different from the definition of characteristic 0 given for a ring. Okay, a ring is said to be a finite characteristic if there exists a positive integer m such that m a is equal to 0 for all a belonging to that ring. That is just like our definition of having finite characteristic. But in case of a ring, if that does not happen, then we say that the ring has characteristic 0. Okay. For us, however, characteristic 0 is a little stronger. For something to be for an integral domain to be of characteristic 0, this condition should be true. MA is equal to 0 must imply that M is equal to 0. If this does not happen for at least one A, then we cannot say it is of characteristic 0. Okay, so that distinction must be understood properly. Anyhow, we are not going to use characteristic of rings as a concept. For us, characteristic is defined only for integral domains having finite characteristic. Or it may be 0. Okay. Because the modified definitions make no sense in the above ring R, means this ring. However, in case of a general ring, characteristic can be defined but locally, and that is using that torsion that we were saying just now. For a general ring, we can define the notion of characteristic locally, that is at a single element. We say that a ring R has n-torsion where n is some positive integer if there exists an element A not equal to 0 in R such that MA is equal to 0 but MA is not equal to 0 for all integers M satisfying this. That is all integers M lying between 0 and n. Then we say that R has n-torsion. Okay, can you see why we are saying this? If you think of A being a non-zero element in the ring R as being in the additive group, then the statement here is saying nothing more than the fact that this n is the order of this element A in the group, additive group. So that means this A has finite order. Okay. Now it turns out that if an integral domain, this is for a general ring, if an integral domain T has n-torsion, even for one n, then D is a finite characteristic. In this way, this is a generalization, because integral domains of finite characteristic are special cases of rings having n-torsion for some n. Okay, so here the section ends. Now we start the exercises. Oh, and this we will see in exercise 8. We will actually prove this. Now next we look at the exercises.